Good morning.
Good morning.
Morning. How's everybody this morning? It's going to be raining all day, seems like.
I'm doing all right. We could use this rain over the summer.
Yeah, that's always the case. Does any of you have classes in person?
I do ROTC at Wright State in person, but it's not really a class.
Yeah. Okay. How many classes are you taking? Was that Matt? Was that you, Matt, or Travis?
Yeah, that's me.
Okay, Matt. How many classes are you taking at Sinclair, and how many at Wright State?
I'm taking basically all my classes at Sinclair. So I've got, I think, 4 classes right now at Sinclair. And then ROTC, there's one class, like typical class that you take. And then we do PT and normal like military training each week.
Okay. So is this your last semester at Sinclair?
Yes, it would be. So I'm going to go to Wright State for 2 years after this, hopefully.
Okay, great. And you'll get an associate from Sinclair?
Yep, that's the plan.
Great. How about the rest of you guys?
I'm in the same exact boat, minus the ROTC thing.
Oh, okay. Okay. Are you taking any classes at Wright State right now or no?
No.
Okay. But this is your last semester here and okay, and then you're gonna go to Wright State.
Yep.
Are you a mechanical engineer too? You going to?
Yes.
Yes, you're gonna be a mechanical engineer. Okay. How about the rest? Logan, how about you?
My goal is to become a mechanical engineer.
Yeah. Are you taking classes anywhere else or just all your classes are at Sinclair right now?
I'm just at Sinclair, but I might start taking classes at Wright State next semester.
How many more classes do you have before you get your associate?
I think like 2 classes.
Oh, after this?
Yeah. I think I have like thermodynamics and dynamics, and then I think it's it.
Okay, so you probably take those next semester.
Yeah. Maybe a summer class.
Okay, that's good. How about Reese?
Hey, I'm actually in the same boat as Logan, but I have a few more classes I have to finish up here at Sinclair. But I'll be, go ahead. Sorry.
Okay.
So, yeah.
And you're a mechanical engineering major too?
Yep.
Okay, and you're going Wright State as well then?
Yeah, I'm in the, I think it's called the Right Path here
Yeah,
at Sinclair. Yeah, the transfer program.
well, that's a great program.
It's aptly named. I thought it was funny.
Yeah. Are you getting any kind of tuition assistance when you go to Wright State?
I think there's definitely some stuff I can apply for.
You know, there's if you get a 3.0 GPA or higher, you get third tuition off. Did you know that?
Oh, I did not.
I'd look into that. That's a big deal, right? I mean, for 2 years, you get third tuition off. As long
Yeah,
as
that'd be nice.
the stipulation is you have to have an associate from Sinclair with it, and then the GPA 3 or above.
Hmm.
And if you go, I would start looking at that now. That's a worthwhile thing to get. That's a lot.
Yeah, definitely.
Okay, how about Miriam?
Well, I'm taking all my classes at Ohio State,
Okay,
except for this one.
okay. You're a mechanical engineering major as well?
I'm civil engineering.
Okay, yeah, I should know this. I have already asked you guys this, but I forget. So civil engineering, okay. And what was the reason you couldn't take strength and materials there? At Ohio State?
Well, I'm currently not in Ohio,
Oh, okay, okay.
so the class, I would have had to go there, commute there, and
I see.
I can't.
Yeah, it was in person. Okay. Plus, it's probably significantly cheaper at St. Clair. And they transfer
Yeah.
it. So it's not an issue. All right. Did I miss anybody?
Dude, I'm doing mechanical engineering, but I'll be finishing up my semester. After this semester, I'll have my associates.
Okay.
I'm still in limbo though between going to Miami or Wright State
Oh, okay. Okay. That's right. You were telling me about that.
because I have over 150 credit hours, but it depends on which school let me have
Yeah.
the most of the credit hours back.
I remember that. So did you go talk to anybody at Wright State?
Yes, they're looking at possibly making me retake chemistry just because it was so long ago, and it was on quarters.
Just one class?
It's just one class. I'd have to retake chemistry and then do the junior senior track and then retake. There's a couple other electives they'd want me to retake, even though I've already redone them at Sinclair.
I would not give up. I would just keep pushing.
I'm gonna have to keep doing that
Yeah, it always
because
helps.
it's the easiest commute for me instead of having to drive all the way out to Miami.
Yeah, I agree. So just keep pushing. Don't take a no. Go see somebody else.
Will do.
No, especially if you know you're doing well. So that should you just tell them. Be honest with them. This is
Yeah, it was just quite frustrating for the simple fact that I'll after this semester I'll have 157 credit hours, and then if you go to them, they're like, "Oh, our degree only takes 127."
yeah. Well,
So I still have the senior track to do, and then
yeah. I understand, but some of those people, I mean, I shouldn't say those words exactly. Some people, it doesn't matter where you are.
yeah, you find it everywhere.
Yeah, they're just so out of touch with the real world that you have to make compromises. You have to make things work. I mean, just because you took chemistry 2 years ago doesn't mean you have to take chemistry again. I mean, it's just make it work.
That's what I'm having to do.
So don't give up. Keep going, seeing people until you find somebody that's a helper.
That I have to make sure that I have the class schedule set up to where I can be full time because then I can use my GI Bill.
Yeah, that helps. That helps. Okay, well, keep at it. If I was there, I would help you get there, but I'm not there. So if I can do anything at Sinclair, I will.
I appreciate it.
Sure. Okay, so any questions about last time? I mean, we went through some derivations. We went through it kind of fast. There was a lot to see and comprehend. Any questions for me about last class? No questions. As far as homework, what was due? When is your homework number 8 due?
I believe it was due today.
Okay, good. That's what I thought. Okay. How did that go? Is any questions about that?
It went pretty smoothly.
Yeah?
Yeah.
It was just a plug and chug, I think.
Yes, it was. Especially the first three problems from chapter 7 that we had us do.
Except the first 3
No,
problems?
no, those three were the exactly plug and chug from the equations you gave us at the end of the class last time.
You mean chapter 6?
Yes.
Chapter 6 was a little bit more. Let's see, which ones did I give you? 6.4. 6.13. Any questions about those? Oh, 6.4. I didn't mean to give you 6.4. I haven't even covered it. 6.4. Oops, that's all right. You did it. 6.22. Okay, so the only problem I didn't mean to I meant to strike out of here. It was 6.4. I have not covered 6.4. But obviously you could have read about it and figured it out, but I have not covered it. So other than 6.4, any questions about any other ones? No? So let's see, homework set number 9. Will be due a week from today. From today be week from today. Oh, we're going to be November 5th. Okay. All right, so let me show you another method. This method is called Mohr's circle. It's based on equations 7.5 and 7.6 that we derived last time. Where's equation? Oh, there they are. Equation 7.5 and 7.6. So I have derived these in my notes. You're welcome to go through it. It's on page 73 of my notes, where I take these two equations, 7.5 and 7.6, and I square them. I rearrange it. So I'm not going to derive it. I'm going to show you the methodology, but I want to go through just a quick background on where this comes from. So I take these two equations. So I rearranged it. I put sigma x prime, and I brought sigma x plus sigma y divided by 2 to the right side. There it is. And then I square every term in the equation. So the left side is squared, the right side is squared. And I do the same thing with equation 7.6. I bring, I guess I don't do that here. Okay, I just square everything. So I have tau x prime y prime squared, and then everything to the right there, is also squared. And then those two equations are added together. So it's not so important to know the derivation, but the outcome is important, and the outcome is the methodology. It lends itself to a circle, and it's called Mohr's circle, for which you can now find stresses at using a circle. And I'll show you how to do that. So let's go through it again. So now we have these equations 1 and 2. We add equations 1 and 2. And in equation 1 and 2, obviously everything related to sine and cosine and theta basically is eliminated once we add them together. So we have the following equation once they're added together. And in this equation, we substitute. We say sigma x plus sigma y divided by 2 is sigma average. And that's exactly what we did in when we did that example problem, if you remember. Our sigma average was sigma x plus sigma y divided by 2. And R, we're going to let equal to what's on the right side here, square root of it. Therefore, we can write that equation 7.9, as sigma x minus, this is sigma average squared, plus tau x prime y prime squared, and then everything on the right is r squared. So this is an equation of a circle. Equation of a circle with the radius r and the center at sigma x prime and tau x prime y prime. That's all you have. And we can find the extremes of the circle. I'll show you how to do that. But it also tells us that the maximum principal stresses are basically sigma average plus or minus the r, the radius of that circle, and tau max is the radius of the circle. So these, and this equation is what Mohr circle is based on, because equations 7.5 and 7.6, once they are once we eliminate theta and add them together and rearrange, we can have an equation of a circle. So loosely, this is where it comes from, the methodology. So now I want to talk about, and I'll show you the methodology. All right, so why do we even do all these transformations? Let's just step back and do a quick review. Why do we even do all this transformations and principal stresses, which are maximum normal stress and a maximum shear stress? Well, first of all, if I have, let's just go back to a simple case. If I have a simple bar, unidirectional loading, meaning just simply I have P in X direction. I have P in the X direction. If you remember, the stress, the normal stress that I'll have, it'll be at, the maximum will be at 0 degrees. And if I just simply take a stress element right there, that stress element will look like this. This is my x-axis. So I'll have sigma x, which is P over A. I'll have, so that would be my stress element. So this is an easy case. Simple one-directional loading. That's what I'll have. And if you also remember, we found stresses in any oblique angle. And from those equations, I found what the maximum shear stress was. And I also found out at that maximum shear stress, what was the normal stress at that plane. And if you remember, that occurred at a 45 degree. At a 45 degree, that's where my maximum shear stress was. So if I take an element at that 45 degrees, so it will be oriented like this. Like that. That element so if this is my x-axis, I have rotated this. This element is at 45 degrees, and so forth and so on. We found out that there was a shear stress on this face. That was my maximum shear stress. And if you remember, it was P over 2A. And if that was there, we had shear stresses in all faces. And we said the failure, if it were to fail, it could fail at 45 degrees, depending on if it's a brittle or ductile material and so forth. So we've talked about that. And then we also said there was a normal stress at this face. We didn't identify all faces, but we just looked at this face. And this was basically our sigma average. What does the book use? Okay, sigma bar for average, which was P over 2A as well. So this was my sigma max, basically my principal stress. Sigma max is my principal stress. Principal stress is another name for maximum normal stress. So this was an easy case. We only had single directional loading, and that's what we had. But here, in the problems that we've been dealing with on chapter 7, or the situation we're setting up, is a case where we have stresses in all faces. Actually, I shouldn't say all faces. It's a plane stress problem, and it's really not in all faces. So it's on two planes. Let's see what page I'm missing something here. Okay, so we had, so what we did last time, we had some structure for which we had, you know, different types of loads, different types of maybe all kind of stuff. And we said, this is a plane stress because all the forces and all the stresses are in X and Y plane. So if we, for example, take a stress element here, it would have sigma X, it would have sigma Y, and it would have tau XY. There's all that stuff. Look, what a big difference, right? From this to this. This was inside the member. That's that element at 0 degrees. So at 0 degrees, this is what we got. So again, we found stress at an oblique angle just like we did for a simple case. And we took those equations and found the maximums. And those maximums are principal stresses. And there is a third one too in the third dimension, which we'll talk about later. So even though we're looking at a plane stress, there exists a Z dimension, a third dimension. And here too, we'll talk about that later, but here it's not an issue, the third dimension. And then there exists maximum shear stress, tau max, and then the orientation. So here, the maximum shear stress occurred at 45 degrees from the x-axis, right? Shear stress occurred at 45 degrees from the x-axis. How about here? Well, it doesn't exactly occur 45 degrees from the x-axis. We'll find that. This, let's go back. The maximum normal stress occurred at 0 degrees. It was in the x-axis. This will not be. So the angle for which, from the x-axis, where the maximal principal stress sigma 1 occurs, because sigma 1 is always greater than sigma 2, and that's greater than sigma 3. This is at theta p. That's the angle at which, from the x-axis, that sigma 1 occurs. And then, so this is the angle. It could be from x or y-axis, but let's just say x-axis. Where sigma 1. And then this is the angle from x or y-axis, but I'm just going to use x. I typically use x, where tau max occurs. So you can see a simple unidirectional stress. It's pretty easy. The normal stress occurs in 0 degrees or same direction as x. Maximum shear stress occurs 45 degrees from the x-axis, at which you have a sigma average. And sigma average occurs in all faces, by the way. But in a case where you have a combined loading, this is called a combined loading, you have multi-axial loading. And this is a plane stress because all the stresses are in a 2D plane, XY plane, 2D plane. There could be, you could have a structure for which you're loading in the Z direction as well. You have forces in the Z direction causing stresses in the Z direction. And we'll deal with that later. So that's what we do. So you can see the analogy, the similarity. We're basically doing what we did before, but in a case where we have a lot more complicated stress condition and we have to resort into more powerful tools, it's not really that much more powerful. It's those equations 7.5 and 7.6 that I derived. The equation 7.5 and 7.6 tell you the stress at any angle And then the maximum of those, we set the, when we solve for the maximums, those are the principal stresses and the maximum shear stress. And in an attempt to solve those, we also need at what angle they occur, and that's what gives us this. So now, like I said, the equations 7.5 and 7.6 will lend themselves, after some arrangement, into a form of a circle. And it's that circle that that I want to teach you today. I want to talk about today. So there are two methods. For finding principal stresses, max shear stress, and theta S and theta P. S stands for shear, P stands for principal stress. And those two methods, first one is this equations 7.5 and 7.6 and other equations that I have derived last time. Yeah, actually, equation, once I take those equations, I've shown you that sigma 1 and sigma 2 are based on equation 7.14, and then tau max is based on equation 7.16 and so forth. So there are, these are not the equations. So I'm just going to say equations. The second method, and this is, as long as you have the equation, it's pretty easy. You just plug in the numbers, right? The second method is called the Mohr circle. And this Mohr circle is based on equations and how these equations lend themselves into a shape of a circle. This is the method that I will test you on. I don't care about these equations. I mean, as long as you have the equations, it's, I mean, any high school student can plug those numbers in and get those. But the method that I will test you on over and over again, multiple times in every exam, is this Mohr circle. So please pay attention and ask questions. And on the exam, I will say use Mohr circle. That's the, if you use equations, I'm not going to even grade it. This is the method, because why do I'm so adamant about this method? Because this method doesn't require you to memorize these equations or even look anything up. If you know the methodology, you can, with a piece of paper and a pencil, you can use this process and find principal stresses and a maximum shear stress and their orientations. So keep in mind, this is the method you need to know. You need to know, obviously, how it comes about, but this is what we'll be doing extensively. So don't think it's going to be just a fleeting moment that you just have to do in one exam. We're going to use it twice. I'm going to give you two problems on the next exam, which will use Mohr circle. And again, I will test you on the final exam. So it's an extremely important method. It's also used elsewhere. Once you use Mohr circle, learn how to use it, you can use Mohr circle for other methodologies too in other classes. I don't want to get into that, but it's a useful method to know. So without do Mohr circle without much to do. Let's see. I'm going to solve that last problem we did using Mohr circle. So this is the example. And then as I go through this example, I can explain. I can explain for that. Okay, so this example, we were given, this is the last one we did using the equations in the last class. Sigma x was minus 40 MPa. Sigma y was 60 MPa. Tau xy was 25 MPa, megapascal. Okay, so this is what was given to us, and we were asked to find the principal stresses. As a matter of fact, for our results, we found the principal stresses and we plot those, if you remember. This is the problem we did last time, exact same problem. We found the principal stresses and the principal planes, the angles called, the angles from the x-axis is called the principal plane. So we use the equations, and at the end, for the result, we plotted the stress, the maximum principal stresses, sigma 1 and sigma 2, and the orientation at which they occurred. 76.7 degrees from the x-axis. Then we also did the same thing for maximum shear stress. We found the maximum shear stress using the equations to be 55.9 plus or minus, meaning plus this way, minus that way on different planes. And then at that plane, we had sigma average, and that occurred at 31.7 degrees. So we have two angles, right? 31.7 and 121. 31, 121. Although the faces at 31 degrees, the face that's under stress is perpendicular to that axis that it's 31 degrees. Same thing here at 121 degrees, 121 degrees, the stresses at that location is the face perpendicular to that axis. So this is part of the solution process. You must be able to plot that. All right, so we're going to do the same thing now using Mohr circle. I'm looking for my compass. For this method, you're going to need a compass. Please obtain a compass. First, I am going to plot. I am going to draw the stress element. That's fine. All right, so this is my x-axis. This is the y-axis. So I have sigma x. I took care of the negative by changing the arrow, direction of the arrow. Sigma y is 60. Tau xy 25. Now, shear stress really doesn't have a sign, but in order to define the direction of this arrow, we put a sign there. So some literature put a sign. Let's say not we. I don't like the sign, but this book uses it. So plus, when they say plus, it means on the x face, it's going up. That's something you got to remember. So that's that. Then we got this. Okay. So that's the state of stress. Okay, so now we're going to draw a circle. The center of the circle will be at sigma average. So on in my notes on page, actually it's after page 73, I think. There's a procedure here. There's a procedure how you do the Mohr circle. So you can follow this procedure. And I have, this is books terminology I'm using here. I prefer just slightly different terminology, but that's fine. Plot the points, plot the center. Okay, so sigma. So these are the important things I want to take from this. So we set up a circle, like we set up an axis like this. So we set up our circle is at minus 40 and 60. Okay, so I need a circle like this. So I set up these axes. The traditional horizontal axis, what we call x, it's now positive normal stress. This side is a negative normal stress. This is tau clockwise, and this is tau counterclockwise. What does clockwise and counterclockwise mean? So, for example, if I'm looking at this shear stress, look, 25, that is going to rotate counterclockwise. If I'm looking at this shear stress, it's going clockwise. So that's what that means, and we'll talk about that some more. In the book, they call this sigma prime and tau prime. I like this better. I mean, you can use books terminology, and I've used books terminology in my notes. But this is how I learned it. This is how I comprehended it, and it's really hard for me to change for whatever reason. So this is that, and then even though I wrote the notes using the book's terminology. So this is the importance of it. So what we're going to do is this. We're going to define stresses. This is called the X phase. So here, this is the X phase right there. And this is the Y phase. The side perpendicular to the x-axis is called the X phase. So this is the X phase. And this one is the Y phase, or Y plane, or whatever you want to call it, Y phase and X phase. I define the axis stresses on those phases. Well, first of all, X phase has so our coordinate system is based on sigma and tau, right? Sigma and tau, right? So this is our coordinates of any point. So I'm going to define the stress on the X phase based on normal stress and shear stress on that phase. Normal stress on that phase is negative 40 megapascal. Shear stress on that phase is 25 megapascal. And now this is where I use clockwise or counterclockwise. Look, this one is counterclockwise. On the Y phase, on the y face, this face. The stress, normal stress is pulling on it. It's 60 positive. Shear stress is 25, but it is going to be clockwise. 25 clockwise. So now I've defined stresses on two faces. The faces of my original stress element that is oriented in the x and y axis. Okay. So now I come to Mohr circle and I plot these 2 points. So based on, so the steps are all there, right? Plot the coordinate axes. Well, I'm calling it this and this, but it's tau and sigma. Positive being counterclockwise. So, okay. So forth and so on, but I like a little different. Plot the point sigma x tau xy, sigma x tau xy, and so forth and so on. So this is what we're going to do. With all the processes there in a different terminology, but this is what I have. So let's see. I am going to mark some points here. Circle is going to get big. All right, so that's going to be too big. So I should have drew that. No, I'm going to modify my. I'm going to make my. The circle is going to be really big, so I'm going to change a little bit my axes. So over here. Tau counterclockwise, positive sigma, negative sigma. All right, that's what we got. So 10, 20, 30, 40, 60. 10, 20, 40, 30, 40, 50, 60. All right, so this is what we got. So each increment represents 10. All right, so I'm going to plot minus 40 and 25 counterclockwise. Minus 40, 10, 20, 30, minus 40. And then 25 counterclockwise is 25 right there. Right there. 10, 20, 30, minus 40, and then 10, 20, 25. All right, so we got that. And then we're going to plot my other point, 60 and 25. 60 and 25 clockwise. 10, 20, 30, 40, 50, 60. 10, 25. There. It's going to be a huge circle. So you can draw this to scale. And I mean, not that you can, you should draw this to scale. All right, so once you do that, you connect the 2 points, draw a line connecting the 2 points and extend it outward. So we're going to connect and extend outward. And this is something, so my methodology is slightly different than what the book uses. And the nomenclature is slightly different than my book and my notes, but I think you guys can adopt my methodology or use books, doesn't really matter. All the same. Not meant to confuse you, it's just I'm more comfortable using the methods I've learned before. So there it is, I connected those 2 points. And I'm going to define these 2 axes. These 2 axes. So I'm going to make a point here. And the point is that, make a note, that all angles in Mohr's circle are twice the angles of the stress element. So, what does that mean? Well, look, X and Y axis are 90 degrees from one another here. Here, they'll be 180 degrees. This point represents the stress on the X face. Minus 40 and 25 is on the X face. So this is my X axis. This point represents my Y face. So this line is my Y axis. Where it intersects the sigma axis is called sigma average. That's my sigma average right there. We'll talk. So this is the origin, basically the origin of my, right. So again, X and Y axis on the stress element are 90 degrees. Here they're double. They're double. I want you to orient it, I want you to identify them. Book does not. I want you to identify your X and Y axis based on the faces of the stress element. So that's what we got. So the center point, sigma average, is where it's the origin. And sigma average is sigma x plus sigma y divided by 2. And the coordinate of this point, the coordinate of that point is sigma average and 0, right? Tau is 0, so keep in mind, we're on this coordinate, sigma and tau. So sigma average and tau is 0. So let's find sigma average. So in our problem, sigma average is sigma x is minus 40, sigma y is 60 divided by 2, so that is 20 divided by 2, it's 10. 10 MPa. All right, so now I'm going to draw a circle. So draw a circle. I'm going to draw, this is slightly different than my procedure here, but it's all the same. Draw a circle with center at sigma average and the radius r. And that radius r is this. This is the radius r. This is r. And we'll calculate r in a minute, but that's r. So I'm going to draw the circle now. All right, so I should extend this. Okay, so that's my circle with the radius r. So let's find what the radius r is. First of all, we need the two sides of this. I'm going to set up, look, I'm going to set up a right triangle. That's how you do it every time. It's a right triangle. This right triangle will have two sides. This side of it is 25. Right? The height of it is 25. The base of it is going to be, let's see, this distance, this is what? This is sigma average is 10, right? Yeah, that's 10. So this is 10. This is 10 from here to here. And this from here to here, we plotted this point, we know the coordinates of that point. This is a 40, right? This is 40. The distance is 40. Obviously it's, so R is the square root of 50 squared plus 25 squared. And the equations also do the same thing, right? 50 squared plus 25 squared, square root of that is 55.90 megapascal. So now I've drawn a big circle with that radius, right? Where the circle crosses the sigma axis, that's my sigma 1. So this circle represents the stress at any orientation, basically, at any orientation. And we're going to gain a lot of information from this circle as we go forward. We're going to use it in other problems. So anyway, sigma 1, this is sigma 2. The maximum shear stress occurs. So the coordinate of, so that point is sigma 1 and 0. The coordinate of this point is sigma 2 and 0. The coordinate of, so I need the extremes of this circle. So let's see, this is the highest shear stress right there. This point, that point is at sigma average and tau max, but this tau max is clockwise. The point down here that point is still at sigma average and it's still tau max, but this is counterclockwise tau max. All right, so those are, and the angles that I need. Okay, so I can find the angles I need in a minute. But any questions thus far? So if that's R, this is R, and also this is R, right? This is the radius of the circle, doesn't matter which is the radius. So I can find sigma 1 and sigma 2. Sigma 1 and sigma 2 are sigma average plus or minus R. Sigma average plus R or minus R gives me that. So let's find those. Sigma 1 will be equal to sigma average was 10, I think. Yeah, right there, 10 plus 55.9, which is 65.9 MPa. Sigma 2 is 10 minus R, which is minus 45.9 MPa. So those are our sigma 1 and sigma 2. That was the radius of the circle. This was our sigma average. And tau max tau max is equal to the radius of the circle. Radius of the circle can also be written in terms of sigma 1 minus sigma 2 divided by 2. Either way, it gives you the same thing, but I already have the radius. 55.9. So it'd be sigma 1 minus a minus sigma 2 divided by 2. So that will be 55.9 MP as well. What else? Finding angles. So there's my sigma max, tau max. Any questions so far? I mean, graphically, you can see all that, right? If you draw it to scale, you can actually measure it. See, look, this tau max is the radius of the circle, and the radius of the circle is from here to here. So if that's 10, I guess you can. You have to measure exactly where that crossed. Well, you can measure this if you do this to scale, but they're raw equations. Just might as well use these. Gives you more accurate results. Okay, so that's what I have, and now I need angles. So there I need two angles. The two angles are theta p and theta s. Well, first of all, I'm going to define them on the circle. So theta p is the angle from the x-axis to sigma 1. That's theta p. I'm going to calculate that. Theta s is the angle from the x-axis. I like to use x-axis. Book does various different axes. They're all the same. Just have to pick an axis and get the angle from that axis. But I like the x-axis. That's why I identify x and y axis. I prefer you use my method. Angle from the x-axis to the closest maximum tau max, to the closest tau max. Why do I say closest? Well, because there are two of them. There are two of them, right? There's one over here, one over here. This is my x-axis. The closest one is this one. I can go from here to here, or I can go from here to here. The closest angle is this. What else? It doesn't make a difference. You can do it to either one, as long as you get the orientation and so forth is correctly, then your stress element will be the same, your maximum shear stress element. But the results will be the same if you use either shear maximum shear stress, as long as you orient the angle properly. Because if I go from the x-axis to the closest one, this is counterclockwise. If I go to the other one, it's clockwise. So I got to keep that orientation in mind. So the arrow starts at the x-axis. Look, I don't have a head of the arrow, right? And the tip of the point of the arrow is where my tau max, the closest tau max is. So this angle, keep in mind the angles on the Mohr circle are twice the angles of the stress element. So I'm going to call this 2 theta s for shear stress. This angle is 2 theta s. The other angle, theta p, angle from the x-axis to sigma 1. Well, there's two ways to get to sigma 1 from the x-axis. Here's the x-axis. Sigma 1 is over here. I can go this way or I can go that way. I'm going to go the closest way. It doesn't matter, as long as you take into consideration the clockwise or counterclockwise of the angle. So this angle I'm going to call 2 theta p. So again, go to the closest route. Any questions about how I identified these things?
I'm good, Professor.
Good. If you follow what I'm doing here and you identify like I've shown, and you do the angles per I have requested, it's a really simple process. And again, if you know this process, it lends itself to doing this anywhere at any time without any books or references or equations. It's all based on the geometry of a circle. Nature is a wonderful thing. Even in deriving equations for stresses, it lends itself to a geometric shape. Okay, so so let's find these angles. We're going to find these two angles. First of all, we're going to do theta s. Well, look, I know the angle from these two, between these two is 90, and I can easily find this angle here because I have the sides of this triangle. I even have the hypotenuse of the triangle. I'm going to call this angle theta. Call that angle theta. And I am going to calculate what that theta is based on tangent inverse of 25 over 50. Keep in mind this side of the triangle is 50, not 40, right? It's 40 plus 10. So, I'm going to find theta is tangent inverse of 50 over 25. Why well, I guess I can call this 2 theta. I guess I can. I don't. Maybe a book does. I'm just going to call it theta. So that angle, do I want to call it 2? I guess it doesn't really matter. I don't have to reference that to anything. But I'll do it 2. I'm just simply calling it 2 theta. So 2 theta is 50 over 25. Is that right? No, I'm wrong. 10 is opposite over adjacent. Okay, so this is 25 over 50. So we can find the angle 2 theta as that's tangent inverse of half. .5650 degrees. Okay, so that's my angle. So if that's this angle, then 2 theta s is 90 minus that angle. Does everybody agree? This is 90 degrees between here and here. So 2 theta s is 90 minus 2 theta. So 2 theta s is 90 minus 2 theta. Everybody's with me on that one?
Yep.
So this 2 theta s, 90 minus 26.565. -90 minus 26.565 is 63.435. And I'm going to find theta s. It's half of that. 31.7175. Oh, and I also need orientation of this, the direction of this angle. So this angle, look, counterclockwise. So I am either, you can put this or you can put counterclockwise, either one. But this is the answer. Either or, you have to have a direction. And this is meant from the x-axis. Well, I can write from x-axis to be more clear. 2 theta p. So I found 2 theta s, right? 2 theta p is 90. The angle from here to here is 90. 90 plus 2 theta s. Does everybody see that? 2 theta p is going to be 90 plus 2 theta s. Again, all from the geometry. 2 theta p is equal to 90 plus, got to be careful, 2 theta s, not theta s, right? Not theta s, 2 theta s. So 2 theta p is 90 plus 63.435. 2 theta p is 153.435. I need theta p, that's half of that. 153.435 divided by 2. 76.7175 degrees. I am carrying it a little too far, but 3 decimals would be good enough. And this is also counterclockwise from the x-axis. And everything starts at the x-axis, see? Okay, I think we have everything now. Oh, no, we don't have everything, do we? Yeah, we have everything. We got all the stuff that we need. We found sigma 1, we found sigma 2, we found tau max, we found sigma average, and we found the orientations of the angles. So in the Mohr circle, you need to identify clearly your x and y axis. You need to identify your coordinate, what do you call these things? What is the x-axis? Is there a sigma axis? We call those what? Coordinate axis, right? Ordinate and something else. Anyway, okay, so that's that. And also you need to identify where your principal stress is, like these points. You need to identify the shear stress points, maximum shear stress points. You need to identify the angles, to identify the radius. All the stuff that I did here is required when I grade your exam or when you do the homework problems. So please be very concise and detailed, just like I have done it. Arrows start to define angles. Start from the x-axis, end, the head ends at the closest shear stress. There are 2 maximums. Again, one over here, one over here. The perimeter of the circle is what defines the stress at any state. See, we are finding perimeters, right? The extremes. So if I want to find stresses at a particular orientation, it's all on the perimeter of the circle, and I'll show you that. Any questions about Mohr circles so far? We're not done yet. We still have to take all the stuff that we just derived or calculated and the plot the actual stress elements oriented at theta p and theta s. But before I go there, anything that remotely raises a question or you have a concern about, I want to answer.
Can I see the bottom of that page real quick? I think I missed something. Thank you.
Are you done with the bottom of the page?
Yeah, I'm good, thanks.
Okay. And you got everything on this page as well?
Yep.
So it looks like I was looking at the syllabus while Matt was jotting the stuff down. We are on week 10, I think, right now, right? This says next Thursday we have an exam. But I'm going to move that to a Tuesday after. Because I still want to cover, yeah, let's do that. Let's talk about moving the, is that okay, everyone? I'm going to move this test. So based on our syllabus right now, we should be having a test number 2, our second midterm, a week from today. I'm going to move it to Tuesday of the 12th week. Tuesday, the 12th week. Let's see, what day would that be? Let's make a note here so I won't forget. So that'll be the 10th. So our midterm 2 is on Tuesday. November 10th. So on Thursday is homework due, and then we'll also review for midterm on Tuesday. Is that okay with everyone?
Sounds good to me.
Sounds good.
Okay, good. Our circle is a major part of your next exam. All right, so we have found a lot of stuff. So now we need to plot the state of the stress. So basically what we're plotting first is these 2 points. We're plotting these 2 points. And these 2 points, well, first of all, I have a reference based on the x-axis, the location of this point. And that is, from the x-axis, I go counterclockwise in the real world, in the realm of the element of the material, 76 degrees from the x-axis. And I end up at this point. So let's do that. So if this is my x-axis, I'm going to do this one first. 76 degrees from the x-axis counterclockwise. Let's see, that would be 90, so 76. Let's just say this is 76 right there. I could draw this to scale too, by the way, right? I can, I don't have, do I have? Yeah, no, I don't. I don't have anything to draw angle properly, unfortunately. But that doesn't matter. I can approximate it. So if that's 90 and that's 45, let's just say this is 76. So here it is. Oh, I went the wrong way. No, that's right, counterclockwise. So from the x-axis, I went counterclockwise, 76, this is theta p, 76.71 or 72 degrees approximately, right? Is that good? So on this face, that's the face perpendicular to that plane. I will have sigma 1. So I'm going to draw the whole square. So this is my, this is where, look, from the x-axis, I go twice that, twice the 76 degrees, 153. I end up at, so think about you're on the perimeter of the circle. You're on the perimeter. You go from the x-axis, 76.71, but in reality, on the Mohr circle, it's twice that, 153 degrees. You end up this point. So that point is on this face. So on that face, we have sigma 1, which is 65.9. I have sigma 1, 65.9. And as far as shear stress, 0. So I am plotting the coordinates, these coordinates, sigma 1 and 0. If that's the case, I have to have sigma 1 and 0 on this side. And how about these faces? Well, look, these faces, look, if I go 90 degrees from this face to this face, I end up here. 90 degrees counterclockwise. Or I can go 90 degrees clockwise. Either way. You guys agree? This from here to here is 90 degrees, right? This is clockwise, this is counterclockwise. So let's see what we got. Well, I'm going from sigma 1. So look, sigma 1, I'm right there at this point. This point represents that face. Everybody see that? Put both of them on here. This face represents that point. All right, so again, this point is represented by this face. Sigma 1 and 0, sigma 1 and 0. So I go 90 degrees either direction. 90 degrees, 180 here in the Mohr circle. So look, 180 degrees either way. I end up exactly at the same point. Sigma 2 and 0. So 90 degrees counterclockwise here equates to 180 degrees here. Counterclockwise or clockwise, I end up at the same point. Sigma 2 and 0. Sigma 2 is minus 49. So on either face, I don't want to do a double negative. In reality, it is, if I want to write it at sigma 2, I am going to put a double negative, 45.9. Be aware that the literature, and I'm not the only one doing this, the literature also does a double negative, right? This negative. Either one you should be able to figure out. Depending on what book you read, somebody will have a double negative like this. Somebody will put no sign here, and it'll show the negative by that, but either way. So both of these are sigma 2, and that's what we expect. This has to be in equilibrium. It has to be in equilibrium. And notice how I define this angle, right? I started from the x-axis, my arrowhead ended up at sigma 1 axis, where sigma 1 is, or principal plane. Exactly like this. Exactly like what I had here. So all that stuff kind of drives, all that works out. Any questions so far? I want to stress one more thing. The book might do this, and that's perfectly fine. It's not my methodology. It gives you the exact same answer. The book might do this. They might say, instead of taking 2 theta p from x-axis to sigma 1, I want to take this to be my 2 theta p. I'm going to call this 2 theta p prime, and I'm going to show you we get the exact same result. So this angle, 2 theta p prime, is the same as 2 theta. Agreed? But it's going from the x-axis to sigma 2, 0. But let's figure that out. So let's write that, and I'll show you it's exactly the same thing. So based on what I have defined, my 2 theta p prime, 2 theta p prime is same as 2 theta, which is equal to 2 theta. I have theta up here somewhere. 26.565 degrees. And notice also the direction of that arrow. This is now clockwise. Clockwise. But we end up where? We end up, if you go from the x-axis, we end up at sigma 2. So let's do that. From the x-axis, clockwise 26.56 degrees, I end up at sigma 2. That's what this says. From the x-axis, I go half of that. Is that the angle? Yeah. I go half of that. So this angle is theta p prime. Theta p prime is going to be 13.28 approximately, and it is clockwise. Well, look, if I go 13.28 degrees, 13 plus 27 is about 90 degrees, right? These sides are 90 degrees from one another. I end up at sigma 2 and 0, which this is exactly the same thing. So if I end up at sigma 2 here, 90 degrees from it in either direction, 180 in the Mohr circle, but 90 degrees in either direction, I get to sigma 1. 90 degrees in either direction to sigma 1. So it doesn't matter. I could use that angle, I can use this angle, but as long as I know the orientation of the angle and where does it end? I end up at sigma 2 here. If I go this way, I end up at sigma 1. So it doesn't matter. I like to do it from the x-axis to the largest principal stress, sigma 1. I like to take from the x-axis to the closest tau max for theta s and so forth. But I wanted to show you that that's exactly the same thing. Theta p prime plus theta p is 90 degrees. Pretty amazing stuff. It gets me. This is what I live for. It's kind of exciting for me. But anyhow, might not be the same for you. But so we took care of this. We want to also plot the orientation of the maximum shear stress exactly at what angle does it occur. Well, we know that. We need to plot it. So this is from the x-axis, 31.71 degrees. And I took half of that, right? This was, yeah. And that's counterclockwise as well. So here I'm going to draw that. Here's my x-axis. 31 degrees. So it'll be more like this. 45 would be like that. 30. So this is This is going to be theta s. Again, this is clockwise. I'm sorry, counterclockwise. So if I draw the faces there, it's going to be a little bigger than the last one. It's okay. This is my stress element. On this face, that face is on the Mohr circle. Is on the Mohr circle. So look, on the I went from the x-axis. This is the x-axis. To theta s. Like I'm going counterclockwise. I get to this point. So again, on the perimeter, I get to this point. Sigma average and tau max counterclockwise. Sigma average, what was sigma average? I have it somewhere. 10, positive 10. Sigma average 10. Tau max was counterclockwise. Counterclockwise. This is clockwise, this is counterclockwise. Counterclockwise like that. So this is my tau max. And that was the radius of the circle, which was 55.9. So if that's the case, I have a sigma average here, and I have a tau max opposite. All right, so that's that point. And then, so I have this point. So look, 90 degrees either direction. 90 degrees here, 180 here, either direction. I end up at this point. So 90 degrees in either direction. I end up on this face and this face, these two faces. So either direction, I end up on top, sigma average and tau max clockwise. Again, I still have sigma average. Either direction gives me the same thing. But the tau is clockwise, clockwise tau. Clockwise, right there. So there it is. This is the entire Mohr circle. It doesn't take long at all. Obviously, it took a little bit of time because I had to explain it, but it's all based on the geometry of this circle, and you're always on the perimeter of the circle. You're plotting these 2 points with respect to the x-axis for principal stress plane. There it is. You're plotting these 2 points for the maximum shear stress with respect to the x-axis, 2 theta s. There. You can draw this to scale, use a scale to calculate these, but why not just use the equations? It's simple equations based on the sides of the triangle and so forth. Any questions? In a nutshell, that is a Mohr circle. You don't need to be memorizing difficult equations.
And you said we're definitely going to see this on the exam coming up?
You're going to see it in every exam from now on. Because, you know, we're going to actually now start getting into analyzing complicated structures, multi-directional loading, so a combined loading situation. And for a combined loading situation, if I want to find what is the maximum normal stress or maximum shear stress, those will be the failures. If I want to know what they are and what orientation they occur, this is the only choice I have. So yes, you're gonna use this from here to the end of the semester. Another beautiful thing about this is, again, like I said earlier, it predicts the stress at any orientation. So if I have fibers of some material oriented in a certain direction, or if I have a weld oriented in a certain direction, and I want to find the strength of the weld or the stresses at the weld, I can use this very easily. I can use this very easily. So how much time do I have? Maybe I can show you that. That will take more time. I'm not gonna. Let's see, do I have an example? Let's see what I got. Yeah, I have to do these next time. These will take a long time. What else do I want to say right now? 15 minutes. Oh, okay. So here we can find that now. All right, let's look at this. Well, I can take this example problem we have. We can expand it. So let's say this particular stress state was inside a piece of wood. So this is a piece of wood. And the loading was such that if we take a stress element, and whatever the loading is, there's some loadings, there's some stuff going on that results into, and I'm not obviously predicting this correctly, it all depends on what's going on, but, and it comes down to, these are the stresses. This was 60, this was 40, and then there was a shear stress. This is the problem we just did, right? And this is my x-axis, this is my y-axis, and so forth. So that's the state of stress we just dealt with. But let's say this piece of wood had it doesn't have to be a piece of wood. Let's say it was a piece of steel. Right. Let's say we wanted to know the stresses. If it's a piece of wood, maybe it had fibers that were oriented. Let me pick an angle. Not coincide with anything I just did here. had some fibers. Or maybe it was a piece of steel, and the steel had welds on it. It started life as maybe, I don't know, maybe it was welded across here to join two material. And so this is the weld. Or it could be a piece of wood with fibers running that way. It doesn't really matter. When we knew the orientation of that weld was 10 degrees, or the fiber was 10 degrees from the x-axis. So in reality, I want to know what kind of stresses are pulling this thing apart and what kind of stresses are shearing at this weld. So I'm going to call this sigma weld, and I'm going to call this tau weld. Because when you weld something together, the two important stresses are what's pulling it apart in tension or compression for that matter, and what's shearing it. What is the sliding shear? So these are the two important stresses we need to find for that particular weld, let's say, or if it was a fiber, for that fiber, orientation of strands or fibers. And a composite material, wood is a composite material. And obviously that occurs 10 degrees from the x-axis. 10 degrees, the fiber is 10 degrees from the x-axis. But that face itself, if I were to do this on a stress element, if I construct the stress element, and this is my x-axis, I need to go all the way to that point. So I'm going to call this theta W. And theta W, this angle again is 10 degrees. But I need to go from x-axis to that particular face. That would be 90 plus 10, 110 degrees. Sorry, 100 degrees. I'm making this up as we go, and I hope it works. Be 100 degrees from 90 plus 10. And it is going counterclockwise from the x-axis. So what is my stress, sigma W and tau W? The weld stresses. Because on the weld, these are the stresses that are acting on it, the maximum normal stress and the maximum shear stress. And if the weld can withstand those, it will be a safe weld. And the weld will have some requirements. How much normal stress can it, if I take a weld and I pull on it, at what stress does it fail? And if I try to shear the weld, what is the maximum allowable shear stress? Those are usually given to me. And if the weld is properly welded, if it's welded properly, it should be stronger than the base material. So the weld should be withstanding, and all the material in the base could be would crack or fail if the weld is done properly. But we want to know that here. We want to calculate that based on stresses on this stress element oriented in X and Y, and we can calculate those based on a given scenario. And I'll show you how to do that later. But for now, I want to use a Mohr circle to determine the stresses here, which are 100 degrees counterclockwise. But in terms of Mohr circle, they're twice that. So there are 200 degrees counterclockwise from the x-axis. All right, so let's go on the Mohr circle. I'm going to go in the Mohr circle, and I'm going to expand this again, go like this. On the Mohr circle, from the x-axis, I am going to go 200 degrees counterclockwise. 200 degrees counterclockwise. Let's see. Is that what I have? That's fine. All right, so here's the x-axis. Counterclockwise is this way, 200 degrees. So look, I go all the way to here, it's 180. And I go, so I'm on the perimeter, right? I'm on the perimeter. and I go 20 more degrees. So I end up, let's say I end up here. So again, I am going from the x-axis, draw a line. Going from the x-axis, counterclockwise, to theta w, which is 200 degrees. The coordinate of that point is sigma w and tau w. Those are the things I'm looking for. The normal stress at the weld and shear stress at the weld. Well, how the hell do I find that? Well, I know this is the radius. This length of this from here to here is r. And based on this angle, the angle from this angle, this remaining angle here, is what? 180, that's 200. So that is going to be 20 degrees, right? This angle. Well, I didn't want that. I want this angle. This is 20 degrees. That angle is 20 degrees. I did want that angle to use. That's okay. And this angle is 26. It's the same angle as this angle, 2 theta. And 2 theta is 26 degrees, 26.57 degrees. So I can construct a right triangle. This is the 90 degrees. So I'm going to draw the triangle here. So I have constructed a triangle. This is R. And we know what R is. R is 55.9. We know we just calculated this angle. This angle is 46.57. That plus that. So the height of this represents tau w. The base of this represents sigma w, right? The base is sigma w, the height is tau w. So sigma w is 55.9 megapascal, cosine of 46.57. Tau w is 55.9 sine of 46.57. Easy as that. Everything is on the perimeter of the circle. Let's see, what do I get? 46.57 cosine times 55.9, 38.43 megapascal, and it's in tension, this one. 46.57 sine of the angle times 55.9, 40.595 megapascal. I need orientation of this. Look, this is on the clockwise. So clockwise. So there's the stress. There's the stress right there. Clockwise. So I got that correct. I drew that. I didn't know that was the direction of it. Clockwise based on that. So if it would have said counterclockwise, I would have gone the other way. Clockwise like this. So those are the stresses at the weld. This is the normal stress at the weld. That's the shear stress at the weld right there. And all predicted based on the perimeter of the circle. So again, the perimeter describes the stress at any state, at any angle. And we'll be using that throughout the rest of the semester. I'm out of, basically out of, I got 4 minutes. Any questions for me? I know I went back and forth, but Matt, I know you want to write this stuff down.
Yeah, I'm good. Thank you.
Okay. Any questions?
I have no questions.
Okay. See how nice this stuff is, how beautiful it is? It's really amazing to me. It's just, and you don't need to memorize anything. If you know the process, you can figure it all out with a piece of paper and some tools, or you don't even need to have, any kind of, circle, what do I call this, compass, or anything like that. You can use a piece of string and a pencil if you wanted to, and draw all this, figure it all out. It's amazing how many students graduate from top engineering schools. I'm not talking about Wright State, top engineering schools, and still don't know how to do this simple stuff. It's amazing to me that I sat next to people from Purdue, Ohio State, what else? All over the place, all the top schools. I didn't have anyone from MIT, but when I worked for GM only hired the best they could get a hold of. And these guys came from all over the country. But it was amazing to me that they still couldn't do a simple analysis like this. Now, how did I get a job coming from Wright State and sitting amongst all these people from top engineering schools all over the country? Because I knew my stuff. Because even though I came from Wright State, I really worked hard to get to learn this stuff. And I know most of you are going to Wright State, but that said, I'm going to put this in perspective. Wright State's not the best engineering school, but at the same time, you can learn. You can learn this stuff. Work hard and learn this stuff. And that's it, I guess. Learn the stuff, and you can be with amongst some of the best engineers out there. Not that all of them were like that, but majority of them were, of the engineers I worked with. Didn't know how to do calculations or figure things out, but still they did it, I guess, somehow. They became managers, or they usually excel at whatever you're good at. That's my philosophy. Anyway, keep in mind, even though you're going to Wright State, that doesn't mean you're not going to learn the stuff. Just do it. Work hard and learn the stuff. Read. The book is all the information is in the book. Any questions or comments from me? I'm kind of rambling on, but kind of reminded me of my 17 year at General Motors. Some extremely talented people there, just like anywhere else. And there are some that are not. So that's it. So you can start the homework. I think you can get started on that. I am going to continue with the lecture next time and finish and do some more examples and get you guys ready to do the next homework set number 9 and prepare you for the test as we go forward next week. We got 2 days to prepare you for the test. Don't hesitate to email me if you have questions, and also please start this early on. I mean, this weekend. So don't leave all this to be done the day before the homework on Thursday. I'd rather you work on it, have some questions for me on Tuesday, and when I do examples, you can better comprehend it based on what you've already worked on. So my recommendation to you is to do the homework problems right now, between now and Tuesday. Okay, that's all I had, unless there was a question.
I have no questions.
Okay. Anyone else? Okay, so have a safe weekend and work on the homework problems, please. And we'll see you guys and talk to you on Tuesday.
Have a good weekend.
Thank you.
Thanks. Have a good one.
You too. Thank you.